blood table. See how good you do on these ones. These are the challenging ones. I don't know why, but these are the ones where I see most people make mistakes. So we're going to randomly select one person from this blood donor survey. And I've already given you the probabilities with ors and ands. So let's see. Let's write the symbols out on this one, because I think symbols are important. What's the probability? Well, what would the equation be expanded here? In symbols. Who wants to give that to us? Andrew.
Probability of probability of RD plus probability of 1.
Okay, perfect. Come down here.
The chart is actually pretty accurate.
I think a lot of their data in the book, it even gives the source where it came from. It is real data. Yeah. Okay, probability of having type B blood. How many had type B? 45 out of 409. Plus Rh positive people. The positive people, these are the O positives, A positives, B positives, AB positive, for a total of 344. Did we double count anybody? Which ones did we double count? The B positive. Because here we counted 37 and the 8. Here we counted 156, 139, 37, and the 12. We double counted these 37s, so that's why we have to subtract them off. And again, the final answer is not overly important to me, because I know you can do that. That's easy. Okay, next one's connected with the word and. Remember, there were two ways to do this. Short and long. What's the short way? Do you remember?
Short.
The chart. What are you looking for in the chart? Cooper? You're saying 139. Just go to the A that are Rh positive. I can see it right here. Out of the whole sample. Because they've got this all broken up for us, we don't have to follow the formula when it's all broken up. We can find the one cell that meets both conditions out of the whole sample. All right, you're going to take a 10-question multiple choice test where each question has 5 choices and you are clueless on the material. Clueless, which means you're going to be guessing. Is that unusual? Yes, that's unusual for you guys. Let's just say. ACT. Anybody guess all the way through that bugger?
I have had folks
guess all the way through.
Usually a 13. Usually, although probability, sometimes they'll squeak a 14.
Yeah. Okay, so find the probability of guessing all 10 correct. How can you rewrite that probability question so that it has either ors or ands in it? Think about it. It's answering each question. So what am I looking for the probability of happening? And. So it's the probability of getting the first one correct, and the second one correct, and the third one, and the fourth one, all the way through. So it's the first correct, and I'm not going to write this whole thing out, obviously, second, and third, all the way through, and the 10th one correct. So what are we doing with the probabilities then if I'm connected with the word and? Multiplying. Okay, are they independent or dependent events answering each question? Independent, because the first one doesn't change the second one's sample space. The second question still has 5 choices. So, what's the probability I guess the first one correct? 1 out of 5. The second one I guess it correct? 1 out of 5. Dot, 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 1 out of 5. What's the quick way to do this?
5 to the 10th.
to the 10th. We're going to take 1/5 to the 10th power. If you actually did that, it's gonna, your calculator's going to kick you into a scientific notation number. Okay? What's the probability of guessing all 10 wrong? This is actually a very small probability too. It's almost impossible to guess all 10 wrong. Even though you might think it's easier. It's a little easy, but it's a very low probability. So it's the same idea though. It's the first one wrong, and the second one wrong, and the third one. So it's kind of the same thing. I'll ditto that. But what's the probability that I guess one wrong? 4 wrong answers out of the 5. So what's the quick way to do this probability? To the 10th. Let's just see what that probability is of guessing all. This one's worthwhile looking at. Ugh.
That's not a bad chance.
10% chance. Well, 11. 10% chance you get all 10 wrong. 90% chance you get at least one right. Okay, next one. In a sample of 1,000 people, 120 are left-handed. If 2 unrelated people are selected from that group, find the following probabilities. I only gave you 1. So we're going to draw a tree diagram to show the sample space for picking the 2 people. The tree diagrams break up the probabilities and they're all right there for you. And this one's kind of nice because you're going to have more homework problems that relate right back to this tree diagram, so you'll be able to come back to it. Good question. They'd have to give us that little information in their search. I guess they could count them. They would not be mutually exclusive. But we don't have that data, so we're going to go with you're either right or you're left. Okay, so 2 events. We're going to pick 2 people. What are the outcomes of my event? Right or left? Okay, I got the left. There's 120 left-handed people out of the 1,000. Do you know how many right-handed people there are? Yep, 880. Okay, 1,000. Now you got to do your second event. Pick another person. So what's the probability that this second person is left-handed, given that the first person was right-handed? Did I say it wrong? No, we're picking 2 separate people. We're keeping the people. We're not putting them back in the population. You're killing me. What is it?
I say 879.
879. Just one of these 880 have been picked out. They're off to the side. That leaves 779 out of 879 out of, I'm killing myself, out of, very good. Whew, that was rough. No, we're not putting the people. We're picking 2 people. Oh, we're not putting the people back in. So the left-handed person, given that the first one was right, they're still all 120 out there, but I'm only picking out of 999. Now down here, we're assuming the first person we picked was left-handed. Now we're looking for the second person to be right-handed. How many are there? All 880 are still out there out of 999. And the last one, there we go. And it might be helpful to tell yourself the outcomes here. Right, 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 left, left, right, and left, left. Okay, I only gave you one probability question here, and it's all about taking it and rephrasing it with ands and ors. And what you're actually what outcomes are you looking for? So I'm looking for the probability that at least one person is left-handed. So how many of these outcomes here have at least one person left-handed? This one, and this one. How do I phrase that, though, as a probability question?
R and L.
R and L,
Or L and R.
or L and R,
Or LL.
or LL. You're getting the hang of it. So I've got multiplying and adding all in one. So we just follow the branches out. The RL branch is right here. So we've got the 880 over 1,000 times the 120. And you guys should be doing it on your own. You don't need to bob your heads up and down here. LR down here. And LL. Plus. Okay, this last one's just kind of fun. Monty Hall game show, before my time, just so you know. I did not actually see this show on TV. What he did, you know, game shows, at the end of the show there was a winning contestant, and he would pose 3 doors to them. Behind one of the doors was a car, behind the other 2 were goats. And, well, you could probably keep the goat. So what he did, you picked a door, he knew where the goats were at. He would then open up one of the other doors. Okay, so now you're down to seeing the goats, you've got the door you picked, and the other door that's closed. He would ask you, do you want to keep your door, or do you want to switch to the other door that's still closed?
Switch.
What do you think he should do? This was in, do you see this? This was in 21. He posed this question that, if you saw the movie 21, he was looking for another person to be a member of that team that's going to go out to Vegas. And this is the question that he posed to the class to see whose mind, without being taught, was thinking the probability way. And there was only one person in that class who knew this. You didn't? Oh, well, you're going to understand it here in about 10 minutes. Okay. So what do you think that probability is? You've got 3 doors. Draw it out real quick here. 3 doors. Okay, you pick a door. He shows you a goat. Big old goat right here. Then he asks, do you want to keep your door or switch to this one? What do you think the probability of winning is if I keep, if I switch, or it doesn't matter? 50%. That's our guess?
No.
No?
Because when you started, you had a 2/3 chance of picking a goat, which would be 66%.
I think you understood the movie.
Once you, so you're more likely to pick a goat to begin with. So since you're more likely to pick one to begin with, if he opens up another door with a goat, then the goat will be left, but 66% of the time should be a goat.
You're going to go to Vegas and rip him off. He would pick you.
Great.
Okay, we're going to go, I actually want to
Good to know it's in the future.
run through a little simulation real quick, and then we'll do the theoretical stuff, and it's actually very easy to see, and he explained it perfectly.
He has more chance of picking a goat the first time. So why would that change then, once he shows you the goat, why is it not picking?
Since you were more likely to pick a goat originally, well, you kind of assumed you kind of picked a goat. If he shows you another goat,